by Page Wizard Games, Learning and Entertainment. It's that time, everybody. Time for more entertainment and fun with your favorite computer scientist, Dr. Daniel Page. Welcome to Dan Plays, where Dan has fun with friends and we talk about all sorts of fun things, including computer science and everything under the sun. No barriers, just fun. This show is funded by supporters on Patreon and Subscribestar. Check out all the fun rewards and supporter access at the links. That's enough for now. Let's get started. Come on, Dan. Let's get started.
Hello everybody, I hope everyone's having a wonderful day so far. I want to welcome you onto the stream. Hopefully everything's all right here on my end. So, before I get into anything today, tell me how you doing. Let me know in the chat. Yeah, it's Tuesday already. Kind of wild stuff, right? Let me get the chat open. That way you can at least hear in on the good stuff.
How are you doing?
Nah, it's going all right. Just getting excited to talk about what we're going to talk about here today. Today we're going to be focusing in on... So last time we met, I was talking about basic graph theory. So we learn, and because some of this I'm going to recap before we actually start talking about today's lesson. So please don't mind. I will do a recap of what we talked about last time, and some of those things I may bring up eventually later on. So keep in mind that even though if you missed last time, that's a piece of cake. Don't worry. The great thing about graph theory, I find, is I would argue, very concrete. There's nothing too scary about the topic, at least until you get into the nitty-gritties of it. But that's a whole other day. We're talking about some elementary stuff, but at the same time, I'm hoping by the end of this, you'll have some appreciation for how you can explore a graph. So, before I get into any of that today, I thought I would just make sure, I gotta do this. That way you know exactly where you're looking for things. So of course, if you're tuning on in and you want to get the lessons or notes after this, or you're looking for the resources that comprise this lesson, you can go to patreon.com/pagewizard. You'll find the link. It'll be dolling around somewhere about over here, actually. Likewise, you can find all these links in the description. I must also stress that today's lessons also can be found in this book, Advanced Data Structures, an Introduction to Data Structures and Algorithms. So this is a collection of notes. You'll actually find that series also here on Page Wizard Games, Learning and Entertainment, the channel. So do check out that. Again, you'll find the resources in the book, or you can find them on Patreon afterwards. I'll be posting these notes for the supporter access and higher. So if you're looking for these notes after, these are from this book. So if you're curious about that, either go check out this book or go to patreon.com/pagewizard and you can get yourself a copy of the notes that I'll be using as the basis for this lesson. So if you want to, say, review this later so you can continue your learning, that is wonderful. Sorry, I'm just getting really excited over here. I'm just going to put this on over here. So, just for a recap, that book is called Advanced Data Structures, an Introduction to Data Structures and Algorithms. And I guess I should introduce myself for anybody that has not met me before. My name is Dr. Daniel Page, but you can just call me Dan or Daniel. I don't need anything too formal. Just call me Prof, whatever you like. It's not a big hassle with me. But anyways, before I get into today's lesson, I also want to make sure I do this in case there's anybody popping on in a little bit later. Maybe they haven't seen that we're live. I just want to make sure that there's at least some opportunity to hop on in without missing everything. So I thought before I get into all of this, I thought I'd just give you a little bit of a recap of where we are when it comes to today's kind of lesson, to just put everything into place. So I must stress that in my previous lesson, I go into much more detail about this. So just keep that in mind. So today's main object of interest are graphs. So if you're wondering what a graph is, so you could think of it as, some people would call this just a network. Now, just before I get too wild into what a network is, because people, when they say network, they mean a lot of things. They could be talking about a computer network. They could be talking about a social network. They could be talking about all sorts of different kinds of networks, where there's interconnections between entities. So in graphs, the way this works is that you have what we call vertices or nodes, and the interconnections between there's interconnections between the vertices and nodes. We call these edges. And depending on what kind of edge you're talking about, sometimes they're also called arcs or links. So these right here are called nodes or vertices, plural. Singular is vertex or node. So don't call them vertexes. You're gonna make your friendly giraffe cry all over their little animal buddies, okay? So just don't say vertexes. That's not the plural of vertex. It's vertices. So these are all vertices here, all of these. And these connections where these vertices meet, like such as this triangle here, these are edges. So those are the edges. So all of these interconnections here, I'm doing this for dramatic purposes, all those are edges. And when we went around exploring basic graph theoretic terminology, we would talk about, say, this vertex being adjacent to these other vertices. That's how you would talk about a neighborhood of a given vertex. So these would be the ones that it's connected to, if you want to use that phrasing, although I think personally it's easier to use the phrase connected to be talking about if there exists a connection via some pathway between two nodes / vertices. So let me just give you also another piece of information. So for those that want just a couple other conventional pieces before we get into this, if you want to talk about a graph formally, so if I give you a graph G, it's a pair VE, where V is usually it's considered a non-empty set. So it's just a collection of vertices. So there's your collection of vertices. And this right here is your collection of edges. Now, the collection of edges can be empty. So this should consist of pairs of vertices. So each one of these is just a pair of vertices. So these are both vertices here. So each one of these in here represents one of those edges over there. And the ones that we're going to focus in on, the ordering does not matter on them. However, every concept I'm going to tell you about here easily translates to the case where the order between these two actually matters. So that's what we would call a directed graph versus what I'm going to focus in on, what is called an undirected graph. One other detail I want to bring up, it's a nice elementary graph theory result, is the following. Sometimes it's helpful to know that if you have a given set of vertices, each one, and then you know how I talked about adjacencies. So we have also this notion of incidence. So we have what we call incident edges of a given vertex. So on a given vertex, there are the edges that kind of are kind of stuck out from that vertex. We would call these incident edges of a vertex. And the number of those is called the degree of a vertex. So for example, if I call this one vertex A, the degree of A is 3. So deg is used to abbreviate degree. So vertices have degrees. So a given vertex has a degree. It's just the number of incident edges. And one natural result that we're going to use later on is what we call the handshaking lemma. Sometimes it's called the degree sum formula. So I proved this in a previous lesson for you guys. Well, we did together. Is that if I wanted to sum over all of the degrees of the vertices, so if I take and sum over, so I take the degree of every one of the vertices in this graph, so I take over all the vertices. So remember, this is this collection of vertices. I'm going to sum over all of them. So I take each vertex out of my set of vertices and I ask what its degree is, but I'm going to collect them up in a bucket, what the sum of those degrees are. this is actually exactly equal to twice the number of edges. One other thing I want to point out is that the conventions for graphs often are that this is a cardinality sign, says how many vertices there are. Often this is denoted with a lowercase n. It doesn't have to be, but it sometimes is. And a capital, like our set of edges, the number of edges, that's what this cardinality or size of means. It's often written with a lowercase m. So for example, here this would be equal to 2m. And you might ask, Dan, why is this true? Well, think of it like this, and this is why some people call this the handshaking lemma, is you ask a question as follows. So suppose that somebody asked you how many handshakes happen to each one of the participants in a party, and say this network here, this graph, represents all of the handshakes that happened. So take note that the true number of handshakes is, in fact, each one of these edges in this graph. So if you ask each one of the participants how many times they shook somebody's hand, notice that this corresponds to the incident edges of a given vertex, which is the degree, right? So if you ask each one of the participants about whose hand they shook and how many, specifically the latter, if you ask them how many happened, and you do this for every one of the participants, remember what I just told you a moment ago. Each true handshake that happens, each interaction that truly happens, is actually each an edge. But the thing is, notice that I'm double counting, because when I ask, say, participant A here in the party for a handshake, notice that when I ask, say, this vertex, which is a party member here, they'll tell me that they shook A's hand. But A already told me that they shook B's hand. So notice that for each one of the edges, you double count it. So it's a basic counting argument, and that's actually where this handshaking lemma can come from. That's one way you can prove it. It's by double counting. So that's one other detail. Another third one, I said there was only going to be one more, but I'm going to mention one other detail, is that often when we represent a graph, this plays a big role in how we design the algorithms or how we describe them to people. So you know how I talked about the concept of an incident edge? So this is something that's going to be relevant for when we start talking about our graph traversals. So when I talk about that, very often I'll have it where, say if I look at vertex A, I want to know each one of the endpoints. That's what we call the vertices that are on the ends of that of this edge. So you imagine I pick this up like a dumbbell and I try lifting it. Some heavy stuff, man. I want to know, okay, so what's on the opposing endpoint of A? So this is the opposite endpoint. So I want to know each one of these incident edges. Very often I would like to just be able to go through them. So normally when you talk about this, you have to talk about how you actually represent the graph. So two standard ways of doing that is one way is using an adjacency matrix, which you can think of as just a table or a two-dimensional array for those that are familiar with programming, where if I give you two say if I give you U and V, and suppose that these are numbers, so each one of the vertices is numbered from 0 up to n-1. So if I were to imagine each one of these is numbered, instead of A and B, suppose it's like 0, 1, 2, and 3 like this, which is the setup for this. And keep in mind, it doesn't matter which ones I label with which numbers, doesn't matter. I must also stress that the way I drew that picture doesn't matter as long as the connections that we have, those incident edges, and the links that are connecting each one of the vertices, that's all that matters. It could have been that I just put 2 way over here and we had some weird crossing over of lines. That doesn't matter. It's the connections that matter. So if I consider each one of the edges, in the adjacency matrix, the way it works is that if this is a 1, or say a pointer to some edge object, or to some vertex object, whatever it might be. In this case, usually if you're doing a more of an object-oriented approach, if I'm talking a little bit more about programming, this would be like a pointer to an edge object that you have stored somewhere in memory. But classically, it just represents that, oh yeah, these two vertices are adjacent. If it's a 1, that means they're adjacent, meaning that the edge, UV, was one of the edges in the graph. And 0 means that that edge is not in the graph. So what you do is you just go through each one of these, forming pairs of vertices like this. So for example, keep in mind, I just came up with this example on the spot here. So I have 0, 1, 2, 3, 0, 1, 2, 3. Here's our empty matrix here, our empty table. And now I can go through each one of the vertices here. Let's say if I go to vertex 0, notice it's adjacent to vertex 3, 1, and 2. So it's not adjacent to itself, but it's adjacent to all the other vertices. So you have 1s here. Vertex 1 is adjacent to 0 and 2. And then vertex 2 is adjacent to 0 and 1. 0, 1. And vertex 3 is adjacent to vertex 0. So that's, for example, how you could represent the graph if you care about using the relationships they have by their adjacencies. So the 1s represent that there is an edge that connects those two. It has an edge whose endpoints are those indices. And notice that the 0s tell you there is no edge there. So for example, if I look at, say, 0, 2, notice that that's telling me, okay, for 0 and 2, these two vertices, there is in fact an edge. But notice that there is, when I look at the 0 here, when I look at 3 and 2, notice that there is no edge from 3 to 2. One other fun detail for those that are interested in matrices, notice that if you look down the diagonal, it's all 0s, but also notice that the top half of this mirrors on the bottom half. So you just take this, you reflect it like this, you have the exact same graph. The exact same entries. So the upper triangle, what we would call that in this matrix, it matches the lower triangle. It's what we call symmetric. So on what we call an undirected graph, it's always going to be symmetric like this. Directed graph, not so much, because the order doesn't matter here, right? The whole point is that V and U, it doesn't matter if V is here or U is there, it doesn't matter. So that's one other detail. One other thing is that notice that I can sometimes have a lot of 0s in that. So another way you could represent a graph is using an adjacency list. So this is an adjacency matrix. Another way is through an adjacency list. In an adjacency list, what you do is you just simply represent the incident edges as nodes. So what you do, instead of having 1s and 0s like this, what if the matrix has many 0s in it? Well, that means that the graph might be sparse, meaning it has very few edges in it. It's closer to linear number of edges in terms of the number of vertices. So in that case, it might be beneficial, for example, to have it where we just simply store the opposing endpoint or incident edge. This can be a pointer to the edge object or that given node object, for example. So you have a list, which is traditionally implemented with an array for each one of the vertices. 0, 1, 2, 3. Don't mind this one. It's not special or anything. I just didn't draw them all equally distanced. Okay. So for example, 0, notice that 0, if you look at that one there, notice that I have 1, 2, and 3. Notice that and I must stress that the order you put these nodes in this linked list, it doesn't matter. So this is just having an array, each with a linked list. So keep in mind, it's a primary collection, then a secondary collection. This one has to be mappable, so meaning that it has a map-like structure. So think of it like a dictionary. In fact, it can be, as long as you have some way of looking up what these entries are, as keys, for example. But you have the secondary structure. Each of these is some list. And if you're not really got any more specialized structure, a linked list will cut it. So 1, notice that 1 is adjacent to 0, and 2. And 2 is adjacent to 0 and 1. And 3 was just adjacent to 0. So that's what an adjacency list will look like. Sorry, I'm getting very excited here. So notice that this just represents the same thing, except now instead of storing zeros, we have nodes that represent the connections between the vertices. Is that clear, everybody? So these are two standard ways. These are other ways that also exist for representing a graph. For example, there's other ones. Some people call them like an edge list.
Seems good.
So a couple others out there that are out there in the wild. There are things like edge lists. Another one is an incidence matrix. So if you're wondering what an incidence matrix is, that's where instead of having it where you have it where these are vertices on one side, vertices on the other dimension of the table, instead you have it where one of the dimensions is the set of edges. So you have the edges that are numbered on one of the columns. And there's a lot of properties that these so-called incident matrices actually have. If you're curious more about this, there's a whole area of combinatorics called combinatorial design theory. I'm not even kidding. Like, you can easily go into a giant rabbit hole all about the structure of these incidence matrices. But yeah, no, so this is just a bit of recap here, so that way everybody's on the same footing, so that when we start talking about how we can explore a graph, you understand we have a network, it has vertices in it, there's links or edges that connect the vertices, what we call incident edges for each one of the vertices. So these are the incident edges of 0, these are the incident edges of 1, and so on. So just keep that in mind, okay, everybody? So that being said, we're going to be moving into our actual discussion here today. So let me know how you're doing today. Hopefully you're having a good day, and hopefully you found that interesting. So this is sort of a short recap of something I spent a few hours talking about the other week. Okay, doke. So the main thing I really want to get at is that today we're going to be focusing in not on these little structural properties. Instead, what I want to do is I want to focus in on how you can explore a graph. Now, in a previous lesson, I did actually go into some detail about how to do this with, for example, depth first search. I'm going to revisit that in its entirety, and we're going to go a little bit more careful through it. So that means I'm going to go through the analysis of the algorithm. We might talk about some things we can do with depth first search, but also we're going to talk about another way of traversing a graph too. Now, that being said, let's get into this, okay? So anyways, today we're going to be talking about how we can traverse a graph. Now, before I can do that, I have to define what a graph traversal is. So just please keep this in mind. So let's talk about what a graph traversal is. So I'm just going to keep it rather high level, keep it simple for us. It's simply a process of starting at a vertex U in the set of vertices in the graph and processing all the vertices and edges. Now here comes the terminology here I'm going to talk about a bit more. All the vertices and edges reachable from you. I'm not talking about like you. I'm not talking about you. I'm talking about that you right there. So let me do an example here. I really want to explain what this idea of reachable means. So let me draw you a picture. Just get rid of this marker here. It's gone. So let me draw you a fun picture of a graph here. So let's draw out a graph here. We have A, B, C, D, E, H, and F and G at the bottom here. So we've got ourselves here a graph, like nice and simple one, I think. Like, I must stress that this is an undirected graph, but I must stress that the concepts I'm going to talk about here, it doesn't matter if it's a directed graph or undirected graph. But the point is suppose I have some vertex U. Suppose A is U. Not you, but that U over there. So suppose that I look at this, and now in a previous lesson I talked about what a path is. So remember, it's just a sequence of vertices for which each one of the vertices in the pathway are connected by an incident edge. So I have to go from one vertex that's adjacent to another one. So for example, A, B, and C is a path, or in this case, it's just simply A, B, and C is a path. Nice, and we call it simple if there's no repeating vertices. So notice here that from A, I can get to H, I can get to B, I can get to C, following some pathway, right? Notice I can also get even down to G here by going down like that. See, so there's a lot of pathways I could take, right? Now, the question is, okay, so what does it mean to be reachable? Now, suppose that I introduced you another vertex here. Suppose I introduce vertex I. Now, vertex I is isolated here. Do you notice it doesn't have any incident edges? There's no edges that connect it to any one of these other vertices. So notice that there is, yes, so the big thing here is that there is no path from I to any of the other vertices. So that implies that this actually is the case that you can't reach it from U, right? Because there is no path from A to I. So we would say that, for example, all of these edges that form this connected component right here, with the exception of I, because I is not reachable from A or U, right? So that's what I mean by reachable. So it means that there exists a path that comprises those vertices or those edges. So what a graph traversal for us will mean is that you have some starting vertex and you ask the question of, we would like to process all the vertices and edges that are reachable from that vertex. And very naturally, you might ask, where does this go? Like, suppose I want to process the entire graph. Suppose the graph doesn't actually, so I wanted to get to I want to process I2. So that would mean that you need to restart this process, so like bootstrap this process, so that you start off at I again. So I'll talk more about this in a little bit, okay? So we're going to start very basic right now. Now, there's at least a couple different ways you can explore a graph. Now, you might ask, Dan, what does it mean to process a graph? Well, what I mean by processing is that we would like to be able to mark vertices. So I would like to be able to go like this, like, oh, suppose I want to visit that vertex. I'm going to call that a mark. I would like to mark vertices, and I would like to label edges. So if I can do that for everything reachable from you, I'll consider that processing the graph. So naturally, you might ask, Dan, how efficiently can you do this? Now, if you have direct access to those objects, as per some discussion we've had previously, each of these, there are ways to represent the graph so that both of these mechanisms can be done in constant time, because you just have access to them. So you'll have some data structure underlying that is representing the edges and vertices, so that you have some mechanism to, say, label them or mark them respectively. So I'll just presume that there's some ability to label the edges and marking the vertices. Nice and simple, right? So that's what I mean by processing. So you might ask, okay, so where are we going to go with this? So just because we're going to be going on an adventure, I better put my hat on. Let me get my hat on. There we go. I got my discovery hat on. We're going to be going on an adventure. Naturally, I need to be able to do that, because you know the hat makes it all legitimate, right? So the first way we're going to look at how we could explore a graph or network is what we call depth-first search. We're going to talk about depth-first search, which I'll abbreviate as DFS. So a very natural question is, okay, so how can we do this? This idea of processing all the vertices and edges reachable from you. So I'm going to use an analogy to help conceptualize depth-first search for you, and I assure you it will be a good time. So the first thing I like to do is I like to think of the graph almost like a maze, right? So think of the graph like a maze. So think of the graph like a maze, a labyrinth. A labyrinth where we have the following. Where what I want to do is I want to use my imagination. I want to imagine that these vertices, each one of them is going to end up being, think of it like an intersection or a dead end, and you can think of the edges like corridors. So you just imagine this like some big maze where these are like the intersections or dead ends in the pathways, and you think of the edges just as corridors. So the vertices are intersections or dead ends in the maze. And you can think of the edges like the passages that connect those. So the edges are passages. So naturally, you might say, okay, so now so Dan, why are we going into this? So I want to tell you a little bit of a story. So this is story time with Dan, okay? So we're going to be talking about how we could do all of this now using this sort of analogy. Now, I use the maze specifically because I like to use the story of the Greek myth of Theseus and the Minotaur. So I like to explain this in my fun, unique way. So here we go. So anyways, suppose that you are going to enter this labyrinth. Suppose it's far more complex than just this. But for our purposes, it's easy enough to just imagine you have this right here as our maze. Now, suppose that you are Theseus and you're entering into this great, deep, overly complicated labyrinth. Yes, dance, magic, dance. Dance, magic, dance. Some will catch that. The point is that I would like to be able to explore this maze so that I don't get lost. Now, to put this all on a cherry on top, I gotta tell you a little bit about a story with this, just to contextualize this. So in the story of Theseus and the Minotaur, just to give you kind of like the brief version, in the only way that I could have fun with. So in the story, on Crete, there's this king, King Minos. And in the story, King Minos is offered a white bull from Poseidon. And in typical Greek fashion, he's supposed to do something with this white bull. Now, the thing is that King Minos decided, hey, look, this white bull, really awesome stuff. I'm not going to sacrifice or do whatever Poseidon would like me to do with this white bull. So instead of doing that, he decides to hang on to it. And Poseidon didn't like this. So through something Poseidon might do, Poseidon causes Poseidon's wife to fall in love with the white bull. And don't ask me how that works, by the way. The point is that I listen, I'm not even going to go into all the gory details, but let's just say it involves a wood-crafted cow that King Minos' wife crawls into, and the white bull and her do the thing. Like I said, I don't want you to go into all those fun details. So the point is that it birthed the Minotaur, the half man, half bull. And in his embarrassment, King Minos puts the Minotaur in this deep, complicated labyrinth. And the question is, okay, so what is he going to do with this labyrinth? It's almost like King Minos' embarrassment that he has this Minotaur, right? It's his shame. So, later on, there was this exchange that was happening between Athens and Crete, where they essentially would offer maidens and young men to Crete, where they would go into this labyrinth where they'd get eaten by the Minotaur. Really grim stuff, right? And Theseus found out about this whole process, and like I said, I'm not going to go into all of the details, and he was going to go slay the Minotaur. So a natural question is, well, how does he do that? Well, with the help of King Minos' daughter, Ariadne, who was besmirched by Theseus, offers Theseus a solution to not get lost in the labyrinth. It's very simple. What Ariadne does is offer Theseus a ball of string. I know it's not quite a ball, but we'll go with it. So what she suggests is that, hey, look, at the entrance of the labyrinth, I want you to take this string and tie it at the entrance. And that way, if you're exploring the labyrinth, you can just unravel the string. And say if you ever get lost in the labyrinth, you could just roll it back up and find your way back to the entrance. Does everybody get the main idea here? So what Theseus is going to do in our analogy is Theseus is going to, whenever Theseus visits a brand new place in this labyrinth, he's going to mark the vertex. And whenever Theseus is going to consider an incident edge, a new passageway in the labyrinth, he's going to label it. Now, the great thing is that Theseus really likes to use really large writing and puts really big X's on the walls so that Theseus can see where he was previously. So Theseus will know when I've already been down a passageway that brings me somewhere I've already been, versus being at a passage that I've never seen before, versus a passage that I have not yet been down, but I can clearly see that I've already been wherever the other side of that passage is. Is that clear, everybody? So, for example here, Theseus may start to tie that string off at A here, at U, and begin to go down to H. So, Theseus would unroll the string. After marking here at A, it goes to H. And he sees there's no more passages. So, what does Theseus do? Rolls that back up to get it back to A. So this is actually how we're going to process the graph with depth first search. So I think it's a good idea we kind of go through this idea together. Now you might ask, Dan, what exactly is the string in this whole process? Now, let me just show you how this would play out. So suppose that I am at A, suppose I start this process at A. I would mark there. Remember, I want to explore the labyrinth. Maybe I might run into the Minotaur. Who knows? The Minotaur may not even be there. I don't know. Maybe Minotaur is an I. I don't know. The point is that Theseus is going on an exploration to explore the labyrinth. So, and I must stress, by the way, if we did run into the Minotaur and we wanted to, say, compute the pathway to get from the start point to the Minotaur, once we find the Minotaur, we already actually have a lot of information to actually know how to find the Minotaur afterwards. So I'll tell you a little bit more about that after. So, if I go to A, suppose that I were to go down to H like we talked about before. Actually, let me use a different color. I was going to use red, but let's go green. I go down to H. Well, you can imagine my string. Imagine my string here. Suppose I start off at A, and I go to H. So I roll out the string and I get to H. Notice that when I get to H, I'm going to mark it there. And then I consider all of the edges, other passageways I could go down. But notice I already gone down all of them, right? This edge is already, this passageway, I've already labeled it, right? So that means there's nothing else to do here. So I'm going to roll back up my string and go back to A. So now I'm back at A. So you can think of this as I'm unwinding. Now I'm going to look at my next passageway. So I'm going to roll out the string, but notice that I do not see that the other side of the passageway has been marked. So I'm going to go down that way. And now, hey, look, I'm here now. So I'm going to mark that. And now I'm going to go down a new passage. Now, keep in mind that if I can find one, I'll most certainly do it. I'm going to go depth-wise into the labyrinth. But the thing is, the string is going to help me know to make sure how to get back afterwards. So suppose that Theseus goes down this way. Well, what did I say? When we get onto the other side, I unwind my string. I'm going to mark it, and then I'm going to look for any incident edges, other passageways. Notice that I've already gone down this one, so I'm going to definitely consider this one instead. Notice there's only really one option here, so I'm just going to keep going. So I'm going to mark D. And now I'm going to go down another passageway. Notice that I can take this one right here. Notice that this isn't labeled yet. And also notice that the other endpoint of this passageway it hasn't been marked, right? So I most certainly can go down this way and I'll find something new. I'll discover something. So I'm going to mark E. Now, I have a lot of choices here. Now, I could go down to F, I could go to G, or I could go to B. Now, in depth first search, it doesn't matter which way you go. That's the beauty of it. It doesn't matter which passageway you take. There is a simple mechanism to prevent you from revisiting places you already went. Let me give you an example of this. So notice that Theseus already marked a big X over here on this intersection here at B. So Theseus already knows, hey, look, I shouldn't go back up to B from here, because I'll get back there if I roll back up the string, right? The string will take me all the way back this way, right? So Theseus is going to label this edge or passageway with a different color instead, because that'll just send me back to where I used to be, right? So then Theseus can say, hey, look, I already went that, I've already been over there. There's nothing to discover over there. So Theseus instead goes down this way. Wait, let me just make sure I got my thread up to date. So I got E over here. And now we're going to roll out the string to go to F. Well, what do I do at F? I'm going to mark it. And then I'm going to consider my incident edges. So notice that I have the green one I've already been to, right? So that doesn't matter. This one here. Let's go along this edge to G. And now we're at G, right? So I've rolled out my string all the way to G. Do you see that the string corresponds to whatever I'm currently rolled out as? Looks like this right now, where I'm at G, I would go back through F, E, D, C, B, and then A. If I unwind the string like this, that'll take me right back to the entrance. Does everybody see that? Now, notice here that at G, I have another one of these passageways. Well, if I went that way, well, I will just go back to E, but the thing is, I already know I'll eventually go back to E if I just wind back up my string, right? So I'm going to label this in this manner, because I know I'm not going to go, I don't need to go back that way, because I'm just going to wind up my string and I'll anyway get back to E eventually, right? Now I must stress as well, there might be multiple passageways that I may actually go down like this, where I have to wind back up my string and then go down another pathway. So this example, while rather simple, I must stress that it's possible that you might unwind this, then there might be another pathway you might go down. The point is whatever currently is going on with my string, it looks like this. Now, does anybody know what kind of data structure, if you were to look at this right here, there's a nice, an interesting basic data structure that looks just like this. Where notice every single time I examine a new vertex, new intersection or dead end, I put it on the top of this. And whenever I run out of options, I take it off. Well, let me show you how this gets wound up again. So watch this. So I'm going to wind up my string. Well, notice that I've examined all the incident edges here. They're all labeled, right? So it means I'm done at G. So let's go back to F. Well, F, I've already examined everything at F, right? Well, now I could go back. I'm going to roll this back up. Now I'm at E. I could roll this back up. I could roll this back up from D up to C. I could roll this back up now from B. And there I am at. I'm at A again. And notice I've considered all of the edges incident on each one of my vertices. And when I've done this, I've returned back to the entrance. Safe and sound. So, has anybody figured out what exactly is going on with this representation of my string? It's actually a stack. So this is actually, in data structures, you'd call this a stack. And this mechanism is actually facilitated if you were to write out this algorithm. You could naturally write it as a recursive algorithm where the stack is built right into your system, just as an example. But you could make your own stack like this. So anyways, that's actually how depth first search works. So one thing I want to point out while I'm here, before we get into the actual algorithm description, is that there's two kinds. Did you see? Okay, notice first that all of these X's are on all of the vertices reachable from my starting vertex, right? Notice that I doesn't ever, because we don't have any pathway to I, right? Furthermore, notice that the green edges, whenever we labeled with a green edge, that meant that the opposing endpoint was not marked, right? But when the opposing endpoint was already marked, I used red, right? We actually have names for these kinds of edges. They have a very nice property. So the green edges, so these ones right here, and as I lose markers, so the green edges here, we call these discovery or forward edges. So discovery, sometimes these are also called forward edges. And likewise, the red edges, as I suggested, are called back edges. So they're called back edges. Because they don't, we label them as back edges because if we were to take them, it will take us back to somewhere that we already were. So keep in mind, we could follow back through the green edges to get back to that vertex anyways. There's no point in going down that route. So hopefully that's clear, everybody. Yes, I'm going to be talking all about that. Wonderful, actually, it's a really nice observation. Notice that is actually something, I'll mention it now. So notice here that those green edges, they form a very nice structure. They form not only what we call a tree, but it spans all of the vertices that are reachable from U. So all those green edges, indeed, they form a spanning tree of forward edges. So we would actually call this a spanning tree in the truest sense if the graph was connected. Notice that we can't reach i's. Notice that, so if we look at this given spanning subgraph, the one where only we consider those that are reachable from U, it would be a spanning tree. Exactly. So let me give you the pseudocode now for depth first search. Very natural stuff, right? So let's try out an algorithm for this, and we'll talk about how we can analyze it, and then we'll see some properties. So I really like the observation that was pointed out. That's wonderful. So let's talk about the algorithm. And there's some nice properties that this algorithm actually has that we're going to see some ways we can use it. I'll mention maybe one or two of them. I'll have more details in my notes, but most certainly we'll talk about those actually in the future. So we're going to call this DFS, and it's going to be given a starting vertex. So as input, we're given a vertex U, which is one of the vertices in the graph. And I'm going to just presume for the sake of our discussion that this graph is already connected, meaning that you won't have a vertex like vertex I, like in our example. It means that when every vertex is reachable from the starting vertex. So vertex U of a connected graph G, which is going to be equal to VE. And as output, now I must stress that the way I've going to describe this algorithm to you, it is not actually going to return anything. Instead, it's just going to modify the graph as represented. So it's just going to be what we would call a DFS traversal, a depth first search traversal. A traversal of G starting at U. So let's walk through the mindset that we had earlier on. Okay. So we have a starting vertex. Well, what was the thing we did every single time, right? We would mark the vertex, and then we would examine all of the incident edges, right? And if we found an incident edge where the opposing endpoint was not marked, that's when we continued our search along, right? Otherwise, we would just label that edge as a back edge, right? So that's exactly what you're going to see happen here. I'm going to describe the algorithm recursively just because I think it looks pretty. But most certainly, you could easily take the same algorithm if you want to replace this with iteration instead of recursion. Just keep in mind what I said earlier, that you could just replace the recursion, which uses the call time or the runtime stack. You could just use your own stack. So you're just going to mark the vertex. And then for every incident edge, so I'm just going to call for every edge of the form UV, where U is obviously the vertex that's being passed along. So we have to compute the incident edges of that vertex. We ask the question, if UV is not labeled, so if that's not labeled, then, so if it's not labeled, then we can ask the question, is the opposing endpoint marked or not? If it's the opposing endpoint is marked, then we know to use what kind of edge? A back edge or a forward edge? Forward or discovery edge? Well, let's consider the case when U is marked. So if U is marked, if V is marked, let's be a bit more precise here. We don't care if U is marked or not. It's V that we care about, right? So if that's the case, then what we're going to do is we're going to label this edge, because if it's marked on the other side, we never went down that route, right? That means that we're going to label it as a back edge, right? Then we label UV as a back edge. Otherwise, we have as follows. We're going to label that edge as a discovery edge or forward edge. I'll use the discovery edge just for the theming of our fun here. So we're going to label it as a discovery edge. And then we just recursively apply DFS on the opposing endpoint, V. And I think I need one more. There we go. So that's DFS, where we're giving a start vertex here. So let me just grab a different marker here. Okay. So are there any questions about DFS, or is this pretty clear? So it's just the exact idea we've been using in our example, and on the same idea we used to explore the maze, right? The labyrinth. I assure you, I will not wear the tight David Bowie pants, okay? So I will hold off on that for today. So anyways, so this is DFS here. I thought it'd be a good idea we just let's do a time complexity analysis. So let's talk about that. So I'll have a bit more of the details in the notes here, but let's walk through this. So I told you that marking a vertex can be done in constant time, right? So this is going to take some C1 many operations. In fact, I'll use a different color to help indicate the parts of the algorithm. So let's use a blue marker. So C1 many operations, some constant number of operations are needed to mark that vertex. Then next, what we have? Well, we have everything inside of here, right? But now notice that this is a recursive algorithm. Now, notice that there's a recursive call right there. Now, a common technique for analyzing recursive algorithm is to start off by ignoring the recursion first, formulating what the time complexity would be without the recursion, and then incorporating the recursion in. For example, how many recursive calls are happening each time, how big are the sizes of the instances. So in this case, let's kind of do that. So we're going to ignore the recursion. So please keep this in mind. We're going to ignore the recursion. That's a little squeaky. We're going to ignore the recursion. So that means that this line right here in the algorithm, presume it takes constant time. So that means that all of this, so remember I have an if statement, I check if it's not labeled. Since I have access to the edge object, I do not need to worry about lookup times other than it being taking constant time because I have direct access to it. Checking if this is marked constant time, labeling an edge constant time. Then we just have this call, but we presume that we're going to ignore the recursion for now. So it means that all of this takes some C2 many operations, right? Naturally, we only have really one part I have not yet incorporated. It's the loop here. Do you see this loop we still have not accounted for this. So we're going to take everything inside the loop in combination with what's on the outside here. And that's actually how we're going to formulate our complexity function. And once we have that, then we can play around with it based on how we represent the graph. So notice that the question is, okay, so we have to determine this right here. Well, it's the number, so presume it's just some number. For our purposes, we're going to go into some more detail. But for us, it's just as simple. It's just going to be the number of iterations times C2, because for each iteration of this loop, it performs C2 many operations. What this will be depends on how we represent the graph. So now we can come together and try to formulate a complexity function. Then we're going to look at how, depending on we represent the graph, comes to our result for the time complexity of the algorithm. So notice I have C1. So it's really just two pieces here. It's nice and simple. We have C1 plus number of iterations times C2. So let's write that over here. And let's figure out what's going to happen when we think about each representation. Okay. So let's put this all together now. So we know that for one call of this, it's C1 plus number of iterations times C2, right? So for one call of DFS, you have it where it's C1 plus C2 times the number of iterations of that loop over there. But there's a very nice property of DFS. Did you notice that we only call DFS recursively only in one situation? And let me just explain this in a very simple way for us. Okay. So suppose that I have this bucket here, and this consists of all of the marked vertices in the graph. Now, suppose that all of these represent the unmarked vertices. Do you notice that in DFS over there, the one we just looked at, notice that every time I mark a vertex, it goes into this bin. It never comes back out of the bin. Why? It's because whenever we examine the opposing endpoint of an unlabeled edge, we consider two cases, right? When it is, of course, the opposing endpoint is marked, we label as a back edge. When it isn't, we label as discovery or forward edge. But in that situation, what did we do? That's the only time we ever call DFS on the opposing endpoint. But that means that every single time I do this, suppose that these are all of these hypothetical vertices that you haven't yet reached. They're all going to go into this bucket, but they're never going to come out of the bucket. So if you actually think about it, every time I mark a vertex, it's like I'm just taking each one of the vertices and I'm just tagging them off and saying, there's going to be at most one time I'm ever going to mark a vertex. That's the big thing I really want you to notice. So what does that mean? So here's the big observation. So here's the observation. The algorithm visits every vertex in G, presuming, of course, it's connected, right? In G exactly once. Exactly once. Thus, how many recursive calls happen, or how many calls just generally happen? The number of calls is dependent on the number of vertices in the graph. So the number of calls is the number of vertices. So that means our complexity function looks like this. It means, so this is the complexity function. So here's the complexity function. So for each one of the vertices in the graph, you're going to perform these number of operations. C1 plus C2 times the number of iterations. So that's what the complexity function looks like. Now that we have this, and you might ask, Dan, why didn't you just make it n times this? Well, you're going to see very carefully that in one situation, your observation is exactly correct. In the other version of this, it's actually helpful to write it like this. So it's best I just keep it general now and then I specialize later. So there's two ways I could represent this graph that I've talked about, the adjacency matrix and the adjacency list. So let's talk about how this plays out for each one. So I'm going to keep this brief here. I'll have more details in my notes. So for the adjacency matrix, please notice that to compute the incident edges over there, so when I look at my loop over there, I go and try to compute the incident edges. That's really what I'm doing. But in an adjacency matrix, just as a reminder, you have it where you have, imagine you have an n by n table, and to examine a row to determine which edges are my incident edges, I need to go across a row in the matrix. But what's one dimension of the matrix? It's the number of vertices, right? And in the worst case, that means you're going to have to look at every one of the entries in that matrix. So computing the incident edges in that case, so to consider the incident edges, consider the incident edges, we must, in the worst case, examine n entries in a row of the matrix, right? Let's write of, let's go in a row of the matrix. Therefore, the worst case time complexity I'm sort of crunching it all in one spot here. Worst case time complexity is as follows. So notice that the number of iterations here is n, because it'll take you linear time to compute that. It'll take the number of iterations. It's going to augment that for the adjacency matrix over there. You're going to need to traverse a row. So that means the time complexity is going to look like this. So let's specialize it now. So for each vertex in V, we have it where we have C1 plus C2 times n, right? Because it's n. Number of iterations is n in this case. But let's see. Okay, well, I have n vertices, right? So now I'm going to just pull that in. So now I have C1 times n plus C2 times n squared. But this is big O of n squared. Which, if you think about it, if the graph is dense, meaning it has many edges, that's perfectly appropriate, right? So that's what you would get with an adjacency matrix. Let's talk about an adjacency list now. So with the adjacency list, it's just a little different, but it relies on your understanding of how we can compute the incident edges in an adjacency list. So in an adjacency list, however, notice that to access the incident edges, we actually have access to that information in an adjacency list. It's simply in one of the linked lists that comprises the adjacency list. So just as a reminder, just here's a little doodle just to help you, remind you of this. So if I look at any one linked list or secondary data structure that's storing the incident edges, suppose it's this one right here. Remember, each one of the nodes is for one of my neighbors, each incident edge in our case. So the number of these corresponds to the degree of a vertex. So to traverse through each one of these nodes, for example, I would have to go through this list. Well, how long is the list? Now, if I was being very naive, I would just tell you, oh, well, all of the vertices could be in that list. That's true, but there's a much more precise way, as I said. So to scan a list, requires traversing the degree of U vertices, or elements. We'll say elements here. So this is why I wrote this in this specific way, to be very helpful. So let me just grab a different marker. I'm just going through markers like crazy. Woo! It's gone. It's gone. So we got ourselves the following. So now all we're going to do is we're going to replace number of iterations with the degree of U. Because that's the number of iterations. Is you have to go through one of those lists when you specialize this. So therefore, the worst case time complexity is as follows. So watch this carefully. So I'm going to I'm summing over all the vertices, C1 plus C2 times the degree of U. Now, notice that the C1 only depends on the number of vertices, right? Notice that U is the only thing that really depends on this sum, right? So I'm just going to pull that out to the side. So I'm going to have C1 times N like I did before. Notice every time I have this in the sum, it's just C2 times whatever I'm adding. So I just go C2 times the sum over all the vertices. And each one is the degree of that vertex. But here's the catch. Here's the catch. One of our best friends pops up here. This looks like something we've talked about before. That right there is the sum of the degrees of the graph, right? But what's this? What is this equal to? We have our friend, right? The handshaking lemma. The handshaking lemma tells us that this is exactly equal to twice the number of edges. So this is by the handshaking lemma. So this is C1 times N plus C2 times 2M. And if you look at this, you're like, okay, well, what's the big O here? Well, notice I have an N there and I have an M here. So I'm going to suppress the constants. And I'm just going to proceed as follows. And I end up getting big O of N plus M. So this is linear in the size of the graph. The number of vertices, number of edges. So this is the time complexity when you represent it as an adjacency list. Yeah, so notice exactly. So notice that, so keep in mind, I'm going to write it like this, but I must stress that if you have many more edges than vertices, it would just be big O of M, right? So I must stress that this is just meant to be clear, so that way we have what N is and M are. Keep in mind that there could be very, very few edges in the graph. I'm just going to keep it general here, but I must stress that if you know more about your graph, you can tailor this even further. For example, just to give you a quick example of what I mean by this, suppose that you knew, this is actually big theta. So that is indeed a big theta. I'm just keeping it simple with big O here, but most certainly it is a big theta. So let me just make one example of this. And this is actually something I've talked about in the past, is that suppose you're given a kind of graph where the number of edges is very few. It is what we'd call sparse. So a sparse graph, for example, is one where the number of edges is big O of N. Something roughly this. In particular, there are certain kinds of graphs that have this property where the number of edges, so the number of edges is big O of n. So you might know some examples of graphs that are like this. For example, a tree has this property. There's what we call planar graphs. I talked about those in the past. Planar graphs, those also are sparse like this. But if you're given a graph that's like this, notice that the m here, you can replace that with an n. So that means that the algorithm runs in big O of n, or even big theta of n, in those specific kinds of graphs. Pretty nice, right? One other thing I also want to point out is that if your graph is dense, notice that this n here, notice that m here will be approaching n squared. So you end up getting big O of n squared, just like you had in the earlier case. So there's a nice connection between the density of a graph, or how dense the graph is, versus how sparse it is. And there's a lot you could go into in detail about this, but most certainly that's one thing I wanted to point out. This is actually the main reason why I wrote it out like this. So depending on what we call graph class it has, there might be more underlying structure you could take advantage of for your graph so you can better understand how efficient it is. Hopefully that is clear. So one last thing I wanted to talk about here, at least for DFS, we're going to keep talking about some more stuff here, is I wanted to talk about something I alluded to earlier on, is what exactly do you do with a graph that you know for certain is not connected? So how exactly do you get DFS to work in those cases? So it's actually really straightforward. This is actually why I introduced the concept of graph traversal in the way I did. Is that if ever you needed to, say, re-examine from another starting vertex, you just apply the algorithm again. So how can we ensure the graph visits every vertex in your graph? So under the presumption that the graph is connected, implying that there is a path between any two vertices, DFS on a single vertex will get everything, meaning you'll compute and process the entire graph. However, if it's disconnected, meaning that there exists more than what we call connected components, then we have to be a bit more careful. So you're going to look at this next one more as a generalization. So suppose that you need to have it where you start up the algorithm again and again and again. What's an easy way of doing that? So how to process the graph if disconnected. So I have some good news for you, is that it doesn't make any difference from a complexity standpoint by adding this extra bit of work. It doesn't make any difference from a complexity standpoint. But it looks like this. So all you're going to do is, if you have any vertices that are not yet marked, just simply run DFS on that unmarked vertex. So you just simply go through each one of the vertices, and you just simply say, hey, look, is it marked? If it's not marked, run DFS on it. So that's basically the idea. It's nice and simple. So let me just give you the quick way of looking at this. So I'm also going to put in a lot of the bookkeeping stuff. So suppose that you wanted to have this thing clean up the graph every time you wanted to run DFS. I'm going to throw that in here too. So this would be DFS where I pass you a graph. So for the sake of brevity, I'm just going to ignore the input-output. Just presume it's a graph and presume that the vertices can be marked and the edges can be labeled. And it's just going to do a DFS traversal of the entire graph. So I'm just going to throw some bookkeeping in here, so meaning that you're just going to make sure that the graph is nice and clean, just in case there's anything that's been mutated about the markings. So for each vertex in the graph, you're going to do the following. You're just going to simply set V as unmarked. So you're just going to make sure it's not marked. And then for each one of the edges, for each edge, make sure so make sure E is not labeled. So just make sure it doesn't have a label on it. Sorry, labeled. Gotta be careful with these little things. Next. Now, this is the part that really matters here. For each vertex V in V, you're going to do the following. So if the vertex V is not marked, if V is not marked, then all you're going to do is you're just going to apply DFS on V. So all you do is you just add in this, and this will ensure your graph is going to be all nice and clean so that when you run DFS, you're not going to have it where marks already exist. Likewise, this will make sure there's no labels that are already on the edges. But the part that really matters here is this last loop right here. You might ask, Dan, what's the time complexity here? It's the exact same as what I had over here, believe it or not. So for an adjacency matrix, it's big O of n squared or big theta n squared. For the adjacency list, it's big theta of n plus m. Now you might ask, Dan, why is that the case? Well, remember, in our previous analysis, we presumed the graph was connected. If the graph is disconnected, that means that when we went through that same analysis over there, that means that we were actually counting up the number of vertices and edges, or the degrees of vertices and edges even, with respect to only one connected component. Because whenever you run DFS on a given vertex that isn't marked, notice that when you start this process up, you're not going into a connected component that's already been explored, right? You're going to some completely new stuff where you're going to look at vertices that have already not been marked yet. Like, remember what we talked about earlier? Those ones are already in here. The ones that this additional calls are going to make are going to be dealing with other unmarked vertices. So when you go through the analysis, what you're doing is you just simply are going to add up all of the time complexities from each one of the calls. But what's that in total? Well, it's just going to be like, okay, each one of the, like, suppose I have like my first connected component, and then I could call that like N1, and then the number of edges in the first connected component is like M1. You can go through each one of them separately. And now you might be compelled when you go through the analysis say, oh, well, this is V, right? Like that's V over there. So that means it's going to be N times this, right? But that's not actually, like, that's a very crude way of analyzing this algorithm. What's actually happening is all the work that's happening within each one of the calls, none of them overlap each other. So it means that when you take the time complexity of each one of the calls, you add them up. It's really just that you're adding up over a finite number of each one of the calls, each of a linear size with respect to the dimensions. Like, say if we're talking about the matrix, like big theta n squared, but each one's with respect to the size of that graph, right? So notice that this is, although it looks like you would just go n times that, it's actually just that literally you're adding up all of the work that's happening. Each one is separate. And over all of that, it's linear. Like, say if we're talking about the adjacency list, it would be big theta n plus n over all of it. But I'll have some more details about it in the notes. But yeah, no, so that's how you could do this. Likewise, one other detail I could point out about this is that if you can easily modify this, for example, so that you can compute the connected components in a graph. So what you do is you'd have some additional auxiliary data structure. And suppose that you want to collect up those vertices and edges, or just say the nodes or anything like that. You can always simply go through and you can augment each one of the vertices. Instead of just having one mark, you can just simply label it with a number. So you can say, oh, this is connected component 1. Or you can have edges being labeled with a certain number as well. You can always augment the data structure or underlying representation so you can number the connected components if you'd like. Or you can even have your own separate data structure that simply says, hey, look, I'm going to store like a list, for example, of all of these edges that are in one connected component. And then I can have those all in my separate collections, each one with their own connected components. But yeah, you can easily modify either way the idea that we literally had by just simply having it where the markings put a number on the connected components. So you just simply have it where it marks it with the starting vertex, for example, if it's, say, an index. But yeah, no, very neat, right? So that's DFS. So let's get the chat open. So, are there any questions at all? Don't be shy. Keep in mind, I'm going to show you one application of, actually, we might have time for two. I'm going to try, let's go for a couple, because I have a bunch. So I was gonna go through a couple. One that's a really easy one, and then one that is more of a utility, like say if you want to compute the pathway, like we talked about earlier. So say if you want to talk about computing a path or detecting a cycle, like we're gonna probably will talk about those two, seeing as those are two pretty common applications. There's other things as well. We'll talk more about those maybe next week even. But yeah, we're going to talk about computing a pathway, which I think is highly relevant to what we talked about with Theseus and the Minotaur. And after that, I think we'll talk about maybe one property that the DFS traversal has. And actually, we talked about earlier on, it was brought up in the chat. It was lovely observation. I liked it. But after that, we'll talk about the other type of traversal we'll talk about here is called breadth-first search, which I think has a lot of fun properties. So many that maybe I'll have to even consider doing a whole stream just on that too. It's a fascinating one. But no, there aren't any questions or anything like that. Don't be shy. I'm happy to answer any questions. Just gonna get this bin and I'm just gonna move this over a little bit so that way I don't bump into it. Okay. So what we'll do is I'm just gonna erase the boards here and then we'll kick into talking about a couple applications of depth-first search. Keep in mind that it's also very easy to modify these for the other traversal method I'm going to show you. So that's also the reason why I want to show you them. Likewise, also this idea. It's also very easy to augment the other traversal I'm going to talk about to make it so it works like this too. So I'm getting very excited. Come on, camera. Let's go over here. Come on. So let me just erase this. But no, if there's any questions, I'm happy to answer any of them. There's lots of lovely things you can talk about here. Some that I'm not even planning, like if you have a general question about something. For example, one thing that I haven't talked about here, I maybe alluded to it the other week, is that there's other ways to represent the graphs. I talked about it at the beginning of the stream a little bit. But there's other data structures that also exist to represent different kinds of graphs. One other one that I did allude to in a previous stream or previous lesson was the idea of a sparse matrix, a sparse matrix representation. So imagine you have an adjacency matrix. If your adjacency matrix has a lot of zeros in it, one way you can represent it is almost like a mesh of nodes. So if you want to have the adjacency matrix-like structure, but you want to have it where it's abstracted over more of a link-based structure, you can use what is called a sparse matrix, which looks almost like a meshing of nodes. I thought I would bring that up. So if ever you need to do like incident edge checks and things like that, one advantage it has is that you can just still access all of the incident edges, but you lose one. Well, one thing you have to watch out for is that you have to sort of set it up so that you have the indexing set up so you have access to the nodes. But the drawback of this is there's many, many links. I mean links in the sense of like a linked structure, like a linked list. Like you have many, many pointers. If you have a very large matrix, there might be a lot of pointers depending on how you set up such a sparse matrix representation. But yeah, no, what was I gonna say? But yeah, tell me about what's on your mind. Hopefully you're having a wonderful day. But yeah, we're going to talk about a couple applications here in a moment. So if you need to get yourself something to drink or anything like that, do it. I'm not going anywhere. I still got a little bit of time here. Because keep in mind, after we do this, we're going to talk about just a couple things you can do with DFS, and then we'll talk about breadth first search, which I have a lot of fun talking about. I'm going to take my hat off for now, just to give myself a breather. I love the hat though. The hat is going to come back on a little bit. No. But yeah, no. Make sure you tell your friends to come on out. We always have a good on time here. No, wonderful. Yeah, no, if you have any questions or anything like that, I'm always happy to answer questions. Also, just keep in mind, depending on what topic it is, I'm usually pretty excited to talk about it. So, for example, I have other stuff on the channel here. Like if you go check out, for example, like on the YouTube channel, I've got a whole series on data structures there. I also have some other lectures out there as well in the wild. But most certainly, if you're looking for more material, just let me know. I'm usually quite happy to make new stuff. But yeah, no, I get that one. As long as you're having a good time. I know that I always have a blast with my students. It's always a blast here. So make sure you tell your friends to come on out. It's a good time. Also, I'm happy to go into those delicate details that a lot of professors aren't willing to go into. Just to be frank, it's one of those fun things that it's just part of the fun here. But that's also because I'm a very meticulous person, just generally. Oh, no, definitely. But no, anytime. So let's get back into talking about applications of DFS. So I'm going to show you a couple ways that you can use DFS. So this is going to be more of like a brief exploration of these things. So I thought I would start off with a simpler one based on our discussion on depth first search. So let's talk about some applications. So these are some classic things you can do with the depth first search traversal. These are not by any means the only ones. There's many. I mean, so many out there that I could easily spend a whole afternoon at minimum just highlighting some of them to you. Here I'm just going to do a couple. Some are far more classic than just these ones. So the first one I thought it would keep it simple is talk about cycle detection. So suppose that you want to detect if there's a cycle in your graph. Another way you can look at this is that if I want to know, if I give you a graph, is it, for example, a forest? Like how do I know if my graph consists of a collection of trees? So one way you can do that is detecting a cycle. And now, one thing that's really natural about exploring a graph using DFS is, let me show you a very contrived and simple example, but it makes my point well enough. So suppose that I have a very basic graph that looks like this. That's 4 vertices, and it's just going to be a box. Now, I'm not going to make it the box graph. I'm just going to make a box that looks like this. So notice that this actually consists of a cycle. This is an example of a cycle graph. It consists of 4 vertices. Some would call this, I think if you count it by vertices, I think it's called C4. But we have 4 vertices here. There's one cycle right here. It's the whole graph. So notice here that if you use DFS, suppose you started at U. Well, what you would do is you would go through the following process. Let me just remind you of how this would work. So you'd mark this vertex. You can go down this way, for example. It doesn't matter. You can go this way. It doesn't matter at all. I'm going to mark this vertex. I'm going to consider my incident edges. Notice I found one that's unlabeled. I continue down that way. I mark this vertex. I consider my incident edges. Then I find one. Oh, look, there's one right there. I'm going to mark this vertex. I consider my incident edges. Notice I have one that's not labeled here, right? Well, what would I label this edge as? A forward edge or a back edge? So would that be a forward or / discovery edge? Or would it be a back edge? Well, look at it. If we are at this vertex currently, but the opposing endpoint's already marked. So that means it's going to be a back edge. A back edge. So that gets labeled as a back edge. So notice here, the reason why we had the back edge is because this vertex already was marked, right? So that means that we have actually a nice, very simple way of detecting a cycle. Why? Because think of it. We already were here, right? So to find a back edge means that I found, if we go back to our analogy about finding our way through a maze, it means I already went down this passage already. So I already went around this way. In fact, I can construct a cycle by following these forward edges to the back edge. So I can form a cycle constructively like this. So the presence of a back edge, I can use this to detect a cycle. So just to kind of summarize what I'm saying here, just to summarize, the presence of a back edge it's saying that the graph is cyclic, meaning it has a cycle, at least one cycle in it. So any cyclic graph has a back edge for its DFS traversal. So that's actually how you can detect a cycle. So let me show you how you could write this in some pseudocode. So I'm going to show you how you can augment DFS to do this. So the thing I really like about DFS is that just like when you talk about some other things like tree traversals and things like that, they work like a framework so that you can pick it up and you can say, hey, look, I want to adapt it to solve this other problem. So if you understand the underlying structure of type for traversal you're using, you can try to see if you can take advantage of properties it has. In this case, it is the way that the back edges and forward edges get labeled. So if I could take advantage of just simply determining when this back edge gets labeled, that tells me if there's a cycle or not. So the minute I label a back edge, I know there's a cycle. So I'm going to call this algorithm hasCycle, and I'm going to have some starting vertex. I'm going to presume the graph is connected. Otherwise, you can adapt the idea that we talked about previously, where you just simply we bootstrap the algorithm again with another unmarked vertex. So I give you a vertex of a connected graph. And I'm going to make it so it's just simply going to detect the cycle. So it's just going to tell me there is a cycle or there's no cycle. So it's going to return true if there's at least one cycle, false otherwise. So it's true if there's at least one cycle, false otherwise. So here we go. So watch this. So do you remember the process for DFS? Remember, we mark ourselves and then we consider our incident edges, right? So that's what we're going to start off with. Because the fact we are marking vertices actually matters here, because that's how we use as a mechanism to know if we need to label a forward edge or discovery edge or back edge. So I'm just going to write out for each incident edge, we're going to go through each one of the incident edges. Each one of them. And then we check if it's not labeled, right? So if UV is not labeled. So the main reason why I'm writing it like this is so that you can see how you can adapt DFS. So like I said, I like to think of DFS like a framework that you can pick up and use to solve other problems. So here we go. So if UV is not labeled, then we had our two cases, right? We check if V, the opposite endpoint, is marked or not, right? We know that when it is marked, we're going to run into that back edge. So if V is marked, then we're going to label UV as a back edge. So I must stress, by the way, that it doesn't really matter a whole lot what we label the edges. What really matters is that we find a back edge. Just the condition of a back edge is that the opposing endpoint is marked. So if we run into this back edge, meaning that the opposite endpoint's marked, we return true. Otherwise, we're going to continue our search. Otherwise, we're going to label UV as discovery edge or forward edge. As discovery edge, then we just check. Now you might ask, Dan, how exactly do we just stop the algorithm from continuing to do the search? Well, I'm just going to do the following. I'm just going to put the recursive call in my condition check. Notice that this returns true. It's a Boolean value, so I could just simply just use that for my logical test. So here's one way I can frame this. I can say if has cycle, which is the name of our algorithm here. If has cycle and I pass it along v, returns true, then you can return true. So this will prohibit you from continuing your search as soon as you find a cycle. So let's see, I just want to make sure I got everything all sorted out. We need to, wait, I have it right here. No, wait, that's for that. Always got to be careful. I have the closing brace, so that's for this. That's for that. And naturally, I need to close everything else up. But after the loop, this is the part that really matters. Is how do we know we don't have a cycle? Well, that means that I had to have examined all of my incident edges, and I didn't find any more options but to say I didn't find a cycle. But I will not know this until I've examined all of my incident edges to see if I've encountered an opposing endpoint that is already marked. Does everybody see that? So I can't conclude that my vertex is a part of some cycle, or at least one of the cycles, until I've examined all my incident edges. So after the for each loop, this is when you would return false. And here's the beautiful part. Notice that if you still think about it, in the worst case, you're still going to have to examine all the vertices in your graph. And all the time complexities we talked about in our analysis of DFS, they still apply here. This is the beauty of just adapting DFS. I said, everything we did to change it doesn't affect the overall time complexity from an asymptotic standpoint. It's just that all I did was I made it so that there's a little bit of a just a little shortcut when we actually find the cycle, or at least one of the cycles. But yeah, so this is how we can do a cycle detection. I must stress that you can augment this with the second application I'm going to show you here if you actually want the cycle. So let me show you the next one here. So that brings me to talk about pathfinding. So how do you find a path in a graph by adapting DFS? How do we compute a path using DFS? So let me just take this and we're just gonna take it one step further. So here we go. So I must stress that we could take DFS and adapt it in many ways. This is just one way you can do it to adapt to find paths. I'm not claiming this is the only way you can find paths using DFS. It's just one way of doing it. So for the sake of completeness, I'm going to mention to you that I'm just going to presume that I have globally accessible to me a stack. Now, this could be if you're actually taking this and picking it up and implementing it. You can imagine this like you have some class, for example, if you're using an object-oriented language. You can imagine this like an instance variable in your class, or even a static variable if your language supports that. So So my presumption, I'm going to presume stack P is empty and accessible to use. So you can think of it as just a global variable if you have a language that supports global variables. The point is it's some stack. And if you remember our discussion from depth first search, you'll remember that I illustrated that when we explored the graph, the string that we use to examine the labyrinth, it corresponds to the stack. So if we make our own stack and we keep track of the path, which represents the current thread of string that we're examining with, then we can actually get a path. But the thing is, I need some way of stopping the search as soon as I find the path, as I alluded to when I was discussing that algorithm. So what I would like to have happen is I would like to have this stack store this path from two desirable vertices, a vertex S and a vertex T. So we want a path from S to T. So these two are vertices, and we'd refer to this as an ST path. So let me give you an example of, just to walk you through DFS, just to see where we can get the idea from, like how exactly did this work. So let me give you a pretty nice, simple example here. I encourage you, by the way, if you want to pick up another example and play around with it, please do so. I encourage you to walk through this carefully. So here we go. So suppose I have the following graph. I have A is going to be our starting one, so I'm going to make it S. Convenient, right? So we have A, B, C, D, and E. And suppose that I would like to find a path. Actually, let's throw another vertex in here, one that most certainly I cannot reach, like F here. Notice that there is, like if I want to go from S to F, that's not happening. There's no path there. So let's think about this. So what I'm going to do is I'm going to take advantage of having this stack P. This is going to be my stack. I could play around with it. So this is stack P. And suppose that I want to find a path from A to E. Now, I must stress that this example is just meant to illustrate the idea. The graph may be much more structurally complex than this. Because this, for example, the structure I have here, technically this is a forest. There's only one pathway from A to E. But it doesn't matter in this at all. So, anyways, let's walk through DFS. I want to show you how I can use the stack just to re-illustrate the importance of why we needed this string to help us unravel to examine the labyrinth and wind it back up when we hit a dead end. So let's walk through this again. So I'm going to mark this vertex, then I proceed to B. I mark this vertex, but remember, what I would like to do is I would like to find a path from S to T. So I start off with A on the stack. So I'm going to push that onto the stack. And then I go to B. Now B may be potentially a part of the path from S to T. So currently I'm at B. So I'm going to push B on here. Now I'm going to consider my incident edges if I'm not T. So notice this isn't T. So I need to keep looking. So suppose that I go this way. Suppose I go to D. Notice that D, there are no more incident edges for me to examine. So that means that I know that there's not going to be, this isn't T, right? So I know this is not going to help me. So I'm going to go back this way. So I'm going to go back up, back to B. So I'm back to B. And now I consider another incident edge. And now let's go to C next. So I got 1, 2. This is the next one we're going to go to, 3. After going to... Actually, let me number these all in entirety. So we visited 3, then we visited 4. Keep in mind, it doesn't matter that we went to D before C. In the algorithm, it doesn't make any difference. The point is it could. But notice that we didn't go there at all. The T's not going to get us from here. We ran out of options. Now next we mark C. And then we follow along here. And we get to E here. After we mark it. Now the big thing. Notice that now we found T. So that we can stop our search. Oh yeah, I need to also make sure we push E onto the stack. When we mark it, we would probably want to push it. Now, if you look carefully at our stack here, notice just like what we talked about previously when we looked at where presently we are with the string we are using to examine the labyrinth, notice here that if you read this from bottom up, there's your ST path right there. A, B, C, E. A, B, C, E. So if you just take this backwards, you get exactly the path. Does everybody see that? Fascinating stuff, right? So this is actually how you can store the path that you find using a stack. So if you make your own stack, you can take this and adapt DFS to find your path you're looking for. So let me read out the pseudocode for this. Nice and simple stuff. Let me just move over a little bit this way. Okay, this will be good enough, I think. Let's just adapt this. So we're going to try to see how this would translate into DFS. So notice that all I really did to change up DFS was I checked if the vertex I was at was T. And in addition to this, after I do this, if I fail to find T, I'm just going to do what I did with DFS anyways. Just the point is I have this stack I'm going to have to maintain. Well, what happens when I hit a dead end and I run out of options and it's not T? This is when you're going to pop the stack, just like I did my example here with D. So I'll show you how this is going to play out. So I have vertices. So now we're going to be given vertices. So let me give ourselves a nice description here. And I must stress again, this is not the only way you can do this, but most certainly this is a nice way you can see how you can take DFS and find paths with it. So for example, you could take this whole algorithm, make it iterative, for example. You'll see that I'm just going to make it so it looks like the DFS I showed you earlier. So I'm going to presume I'm given 2 vertices, S and T. And it's going to output true if there is a ST path. False otherwise. The point is that the stack P will store the path after when I'm done. So if you're wondering, where's the path, Dan? It's in P. So you just go look at P. You could pop off the path when you're done. So remember, like we usually do, we mark the vertex. So we mark S. But you're going to feel, here's the neat part. When we do this, you're going to see it's almost like S is going to move along with our exploration. So it's almost going to, like we're hand-holding S to T if there is a path. So that's sort of how you can look at the recursion that you're going to see here in a moment. But it's not literally that. To just be very clear. So we're going to push S. And as I said, we're going to check if S is equal to T. If it is, then we're going to return true. That means we're done our search. Otherwise, we consider all the incident edges. For each edge, SU. we're going to do the following. Now, one thing you can do with DFS, you notice how, like, here, it didn't really make any difference if the edges were labeled or not. So let's just not care about it. So this is another thing you can do with DFS and all these other graph traversals, that if it's not relevant to label the edges, you don't have to. Just like if you really care about the edges, but you don't care about the vertices, you may not necessarily need to mark the vertices. Depends on what you're trying to solve. But the point is that you can strip away those details if you need to. So if U is not marked, because remember, we want to make sure this thing actually terminates in finite time. We need to make sure we don't simply keep redoing the same work over and over again. If U is not marked, then all we're going to do is we're just going to call recursively pathfind. So we're going to use the same trick we just did a moment ago. If pathfind, and I call it on U and T, so I'm going to advance it one step forward at this call. So pathfind UT. If I'm successful at finding the ST path, then I'm going to return true. Then we return true. Then that's the end of the for loop. Now, if I run out of incident edges to examine and I fail to find the ST path at this stage, keep in mind this will take me all the way there if I need it, akin to what we discussed previously. If it fails to be the case that our node actually advances us to that search, we're going to pop it. We're going to pop off that node, and we know that we've hit an end that is not going to get us to T. So we return false. And that concludes the algorithm. And again, like I said, all we've done is we just took out elements of DFS. Everything else that we did here, pushing and popping on a stack, can be done in constant time, if we presume the appropriate representation for the stack. If, for example, you're using a linked list for your stack, these two operations here will take constant time in the worst case. If you know how many vertices are in your graph, even using an array-based implementation will be good enough if you know how many nodes there are in your graph, which is something it's easy enough to keep track of as some instance variable. But yeah, no, so this is how you can adapt to find a path in a graph using depth first search. So let's head to the chat here. Are there any questions? Any questions at all? Was it clear, everybody? But yeah, no, so we just seen a couple basic ways we can use DFS. I'm actually looking quite forward to our next graph traversal algorithm. So please, if you have questions, put them in the chat. I'm really happy to answer questions. Keep in mind that I do have the chat in front of me. So as you're talking or anything like that, I do see it. And also I must stress that if, say, for example, because keep in mind that I'm doing this over several different platforms. I know, for example, say if you're watching on Twitch, for example, on Twitch, there's actually text-to-speech. So if you're wondering when the text-to-speech gets triggered, it's only when the chat is available on the screen. So must stress that even if you don't see the chat on the screen, I see it right there. So just be clear, don't worry, I see what you write, and it makes things fun. So if you have questions during the lessons and everything, just put it in the chat. I see the chat. But this is usually the best time to answer more complicated questions, because then that way we have some more breather in between things. But yeah, no, so far it seems to be going good. No, I'm excited. I'm very excited. Because we're just about to our next traversal algorithm here. This one I'm quite excited to show you, because it's one of those ones where it has so many lovely properties that it makes it feel like, hey, look, do I need all of this extra stuff that DFS has? Well, suppose that I could layer on top of that some extra properties that it does have. And that's really where we're going with the next one. But the point is here, I'm not going to focus as much on how you can use them and some of the more delicate details around these properties. That I will be talking about in the future. So, or if you have questions, I'm happy to talk about it. So just keep in mind that it's not that I don't want to go into those fine details, it's just that you have to ask me. I'm happy to talk about it. Okay. Yeah, I'm really excited to talk about our next topic here. So, anyways, why don't we get into talking about our next graph traversal algorithm. Like to think of these like a framework. So anyways, we're going to talk about our next graph traversal algorithm. It is what we call breadth first search. So let me write that up on the board here. So breadth first search, which I'll abbreviate as BFS here for our discussion. So, I want to imagine a situation. Now, okay, I guess before I get too far into this, I need to get my hat because we're going to go on an exploration. Let me get my hat on. There we go. There we go. I think I'm ready for doing some exploring. Now, I want you to imagine that you're entering into a deep, dark, dangerous jungle. So suppose here's me. There's me. I'm right there. That's me. You can't really tell. It's rather round though, and it's dark. So you know it has to be me. You see my hat so you can look at this like a sky view. That's me wearing the hat. So what I would like to look for is what I'm going to call the Lost Temple of Awesome. So I hear they have really good gummy bears and chocolate chip cookies. So here's the Lost Temple of Awesome. See, Lost Temple of Awesome. So I'm looking for this Lost Temple of Awesome, and I see that there's some pathways I can take. So now keep in mind, I don't necessarily know how to get to the Lost Temple of Awesome. Now suppose that there's some pathways that I could potentially take to get me through this deep jungle to the Lost Temple of Awesome. But here's the catch. Here's the catch. There might be some scary jaguars out there. There might be some scary jaguars. That they always like to come out at nighttime, and poor Dan's looking for the way to get to Lost Temple of Awesome. See, this is the ferocious jaguar. And I want to avoid the lost jag. See, like they're very elusive. They're just all over the place. So we gotta be very careful not to run into the jaguar because they really bite. So me right here, I'm trying to find the Lost Temple of Awesome. We're gonna watch out for those jaguars. Now, in depth first search, now I could take a depth-wise way of exploring this jungle, right? So, for example, I could take this pathway and go as deep as far as I can along these pathways. But here's the problem. Notice that if I do that, I might take this really long pathway and the jaguar might be right over here. Its big pointy teeth. It might be way over there. And I don't want to go down necessarily that pathway and And what if I do? Like, the point is that I might take this really long pathway when it actually might be that it's just right here. Or just as another example, it could be the case that maybe I go exploring this way, but maybe I take this route instead. Now, suppose that I would like to explore in a different way. Instead of going depth-wise, suppose I want to explore breadth-wise. Now, what do I mean by that? So instead of taking the string, the ball of string that I had previously, and unrolling it as I explore, and then whenever I hit a dead end or no more options I can explore, I roll it back up. Instead, I'm going to use this. And I'm going to imagine I put this like a peg into the ground. And I measure out a certain distance from the peg. It's like if I was surveying. And I look everywhere within that radius and see if I can find what I'm indeed seeking. So for example, I'll go take 1 step into the forest. I'll take 2 steps. I can take 3 steps in. I can take 4 steps in. I can take 5 steps in. And 6 steps in. But as I do this, I can explore more of the jungle. But I do it from my starting point, and I take steps in, and I explore everything breadth-wise. So I examine these, you can almost see it like I'm exploring by expanding my search out along these pathways. But I only do it a certain distance from the start. So I don't, for example, go on a long trip over here to Mochi the jaguar. I don't do that. She'll go and she'll come get me. Instead, what I would do is I would take this route. I would try to expand out my search by taking steps into the jungle, but doing it breadth-wise. That way I can look at my alternate paths, and there's one lovely property that this approach has, is that if I'm always taking an equal number of steps in, and the distance on these paths don't really matter, meaning that it's not weighted, it's not like a true distance, it's just the number of links I can take to get to the place, I can actually minimize the length of that path using this approach. So this is actually the core idea of breadth first search, is that instead of it being where I just go running, be like, oh, I'm going to go into the jungle, I try to go as deep as far as I can with my ball of string. Instead, what I do is I survey and I take steps in and I go around each time. And here's the neat part. You know how I drew this analogy of using a stack for depth first search? The thing that makes the reason why the string operates like that when we talked about solving the maze or exploring the maze, to be a bit more precise, is because the string was operating like a stack. Well, what if I want to have it so it explores all of the vertices that are 1 step away from me, then the ones that are 2 steps away from me, then the ones that are 3 steps away from me, and when I talk about steps, I'm talking about the number of edges that you use to get there. You don't use a stack, so instead of using a stack, you use a queue. So you use that in DFS. We use a queue, which is another one of these classic abstract data types or data structures. So one thing I want to point out about our exploring process is that, again, we're going to label edges, we're going to mark vertices, and again, using the same setup we had previously. But one thing I need to stress is that I'm going to label edges as 2 kinds. So we're going to still have our discovery or forward edges. But we're going to have instead what we call cross edges instead of back edges. I won't go into detail today why we call them cross edges, but the point is that they're going to facilitate a purpose very similar to the back edges. In fact, in a lot of the applications I've talked about, it would serve the exact same purpose. But the point is that when we explore a vertex, instead of it being where we imagine it almost like every time I find a new thing, I push that onto a call stack or just a stack. Instead, I'm going to enqueue it in or enter it into a queue so that those that are closer to me, they get examined first, not later. So let me do an example of what I mean by this, then we'll see what the algorithm looks like. So each time we enqueue a vertex, a vertex, we mark it so that it can be explored. So it will be explored upon being dequeued or when it leaves the queue, when it gets its turn. So you might ask, now, why is that really important? Why do we have to mark them before we put them into queue? Okay, so let's think about this. Suppose that you were exploring it akin to what we talked about there. Well, imagine you re-encounter the same vertex or node again. Do you want to do anything with that node at that time? No, right? We want to hang on to it for when we need to look at it at the time for which we first encountered it. So that's the other important detail here. So let's do an example here. So I'm just going to draw out the graph here. Four, 2, 5, 3, 3 to 5, 4 to 5, 6, 4, 7 to 8, 4 and 6. And we're going to need a queue. So we're going to have the front of the queue, and we're going to have the rear of the queue. So remember, in a queue, when you enqueue, goes on the rear of, just think of it like you're waiting in line. You go to the back of the line, wait for your turn. When we dequeue, comes off the front. So please keep that in mind. Now, one other detail I would like to take advantage of is that I'm going to augment the representation here a little bit. I'm going to have it so that, this is more of a matter of discussion here. I'm going to have it so that we store parents, so that we could have a discussion about what underlying structure might be hiding in this thing. So each one of the nodes is going to have a parent attribute. All of them I'm just going to set to null or nil, whatever you would like to call it. It's not anything right now. That's the point. So each one of these I'm going to make its parent nil. Nil, and our parent here, I'm going to make that nil as well. This is going to be relevant later. So the point here is that we're going to have this be facilitated in a very similar way that we had before. Instead of it being a stack, however, it's going to be a queue. So as long as you understand that how waiting in a line works, that's all we have really here. So I'm going to label the edges in a way akin to what we did before. So I'm going to need my red marker and I'm going to need a green marker. Oh, this one smells like green apples. I'm not even kidding. It's scented. But don't do that with normal whiteboard markers. That is your advice for the day. Don't huff markers. If you find out anything after this and you're like, what the heck did Dan say? Now you know why. So anyways, we're going to start off here at 1. So this is going to be where we're going to start this process. So I'm going to start off by marking 1. I put 1 into the queue. So that's what I start off with. I'm not going to do anything with its parent at this stage. I'm just going to assume it's just initially set like this. And now, what I'm going to do is I'm going to ask, while this queue isn't empty, I'm going to just simply pull off, I'm going to do a dequeue, and I say, okay, well, let's look at doing something with this vertex. And I say, okay, well, if there's anything I have to do, I would do it here. Then what I do is I go through each one of my incident edges. If it's not labeled, there's 2 possibilities. If the other endpoint is not marked, then you know right away you have a discovery edge like we had before. And then what I do is I'm going to take this vertex 2, I'm going to end queue it, and I'm going to mark this vertex. So that when I come back to it, I know that it will be only because that was the first time I encountered it. That's an important detail. That's the first time you come into it. Come into contact with it. So next, I'm still going through my incident edges, by the way. I'm not going to go to 2 and keep exploring from there. I'm still going to go through all my incident edges. Remember, I'm going to take 1 step toward or 1 step into my graph. Remember, think of me going through the jungle, watching out for Mochi the jaguar, okay? So next, I go through my next incident edge. Notice that this one isn't marked. The opposing endpoint isn't marked. So I'm going to enqueue it, 8, and I mark it. Now, I have no more incident edges to consider. So I'm done with 1. So now let's go to our next one. We're going to dequeue 2. So presently we're going to process 2. Now, one thing I want to point out before we get too ahead of ourselves. To get to vertex 2, I used vertex 1, right? So I can always keep track of that information when I encounter these vertices, right? So suppose that I wanted to know which vertex I came from, its predecessor or parent. I can keep track of that information as soon as I first encounter it. So when I initially enqueued them, I could have kept track of that information. Just a little note. So now, let's go through 2. Let's go through our incident edges. There's this one. Well, I haven't been to this vertex yet. I'm going to update its parent because, hey, look, I found it. I'm going to mark it, and I'm going to enqueue it. Then next, I'm going to consider 4. Because remember, I go through all my incident edges, right? I don't proceed to the next one in the queue. So next, I found 4. Its parent is also 2. I mark it. It gets enqueued. I go through this incident edge. Oh, look. This one's already marked, so I'm going to mark that with red here. This is what we're going to call a cross edge. So that's going to be a cross edge. There's something interesting that goes on with these cross edges that I'm not going to go too much into, but most certainly you can think about it. But notice I don't enqueue 8 because we already have 8 in the queue. That's the big thing. Remember, I'm going to get to 8 eventually. But I got there when the very first time I encountered it, I used one edge to get there, not two edges. Just like in my analogy over there where we explored through the jungle, I wouldn't go back to where I originally was, right? I already looked there. So next, we're done with 2. Let's go to 8. So let's DQ 8. So 8 is presently what we're looking at here. We go through our incident edges. Those are labeled. Okay, we got this one here. Okay, cross edge or discovery edge. Well, it's already marked, so we know we aren't going to do anything interesting with that. This right here, that isn't marked, so we're going to most certainly we have a discovery edge. We're going to update parent to be 8. We're going to mark it, and we're going to NQ7 into the queue. And now I've looked at all my incident edges. We're done with 8. Is that nice? So now, so far, we've gone through 8. Now next, we've got 3. So let's DQ 3. Let's look at our incident edges. We have one right here that is not yet been examined. Its opposing endpoint is not marked, so we're going to mark it. We're going to update its parent to be 3, because that's the opposing endpoint here. And I'm going to NQ that in there. And that's all the incident edges for 3. Let's consider 4. We're going to DQ 4. That's labeled. That's not labeled. But this is already marked, so I'm going to label it as a cross edge. And then that's, well, I haven't been to that one yet, so let's go there. Well, I'm going to hang on to it for later, so I'm going to update its parent to be 4. So 6 is going to go in here. I've already marked it just now. Here I've already been there, so I'm going to label this as a, what kind of edge? Forward edge or cross edge? A cross edge, right? And now we're done with 4. Now we DQ 7. Well, this is the only incident edge that has not been labeled yet. Is this discovery or a cross edge? It's a cross edge, because this is already marked. And we're done with 7. Next we got 5. Nothing interesting happening. All the incident edges are already labeled. Same thing with 6. And we're done. We've processed all the edges and vertices that are reachable from the start vertex. One thing you might ask is, Dan, why did you label all of these parents? Now suppose, just for the hypothetical reason, that you wanted to say compute a path. And I must stress, the reason why I'm also showing you this is that if ever you wanted to adapt, say, depth first search, and you wanted to use an iterative approach there, you can also adapt something very similar to this, where you hang on to parents like this, so that if you needed to get any one of the pathways, you could follow these parents. So for example, suppose that I wanted to get a path from 1 to 5. Well, notice that I could just follow the parents from T. So suppose I did run into T. I could just simply adapt to what I talked about previously in our applications of depth first search, and you'd use the same idea. So you just simply update the parent. So you just have a loop where you just check while the parent is null. It's not null. You just follow each one of the parents. It tells you where to go, and you eventually get back to S. So that's why I wanted to show you this. It's an interesting curiosity, but this is also a nice idea if ever you wanted to, say, compute a pathway. But yeah, no, so this is the idea behind breadth first search, is we always take in 1 step, 2 steps, 3 steps, 4 steps. In fact, I'll show you right now what I mean by this. So let me just get these markers put away here. Sorry, I'm getting really excited here. Okay, I'm just getting covered in green apple whiteboard marker. Okay, I'm going to show you something that's interesting that's going on here. Now, where did I stick that blue marker? That's not the blue marker. It's gone. But anyways, let me show you something fascinating. So watch this. Do you remember how this worked? Because of the way we employed the queue. I want to show you how Dan's exploration to the Lost Temple of Awesome, when I take 1 step, 2 steps, 3 steps, 4 steps, is exactly what's happening over here. Except not literally. So notice that when I start off at S, I use 0 edges to get to S, right? So we would call this level 0 or layer 0 in a breadth first search. Notice that I used 1 edge to get to 2 and 8 like this. We would call this level 1 or layer 1. So we'd call these layers or even levels. Usually levels is more common terminology. Now, when you go from, say when we started exploring from 2, notice that the order, because of the way we use our queue, notice that the number of edges to get from 3 to 1 is exactly 2. Number of edges to go from 4 to 1 is exactly 2. And the number of edges to go from 7 to 1 is exactly 2. So we call that level 2 or layer 2. And these are the ones that take 3 edges to get to. So this would be called L3, layer 3, level 3, whatever you'd like to call it. So when we do a breadth by search, what's actually happening is it's just like what I said when we went out into the jungle where we're looking for the ferocious Mochi the jaguar, okay? So we take 1 step in, then 2 steps in, then 3 steps in, but notice that the queue facilitates that we take in 1 step, then 2 steps, then 3 steps. One neat property about this that I'm not going to prove here is that when you look at this, as we've talked about briefly when we talked about depth first search, a lovely person had put it out in the chat, is that you end up with a spanning tree if this is in fact connected. So those green edges, the discovery edges, again, like in depth first search, will form a spanning tree. But here's the neat part about breadth first search. If I wanted to find an ST path, akin to something we talked about in the past, using breadth first search, however, this tree that we've constructed, which is called a breadth first search tree, by the way, this tree has a very nice property. Because of the way we explore level by level like this, the levels in the tree actually tell you how many edges you need to reach a vertex at minimum. So these dictates actually shortest ST paths. So for example, if I want to get the shortest path from S to T over there, I need at least 3 edges to get there, and this is one such shortest path. So this is one benefit that breadth first search has, is that it gives you what we call a shortest path tree in an unweighted graph. Another way you can think of this is if your graph had weights for the distances, like these actually were distances, you can imagine this as if all of the weights were the exact same on every one of the edges. You can use breadth first search like this to compute shortest ST paths. Pretty fascinating stuff, but that's a property of the breadth first search tree. Depth first search also has a tree like this, but it's not the same structure. You can't claim that it computes shortest paths. But breadth first search trees most certainly have this property. So I thought I would, let's talk about the algorithm now. Let's put this all together now. So now we have the idea of what breadth first search is, and how the exploration breadthwise operates. Now we got that, so let's talk about and describe this in pseudocode. And then we'll do the analysis. Okay. So here we go. So algorithm, we're gonna have the same setup that we had before. BFS, we're gonna have a starting vertex. We're gonna have a vertex U of the set of vertices of a graph G is equal to VE. And for output, we're going to have what we call a breadth first search traversal. What we did over there is what we call a breadth first search traversal. So we're going to have a BFS traversal start of G starting at U. So I must stress that if you want to have it where it examines the entire graph, you're presuming that the graph is connected. That means that there exists at least one path between any pair of vertices. So here's the setup. So what you do is you start off with a queue. So you initialize an empty queue. You have your queue. I'm going to write this one iteratively so that you get an idea of how you could perhaps pursue depth first search in a similar manner. So just to give you a flavor for this. So we enqueue in the starting vertex at our given call. And then we're going to mark it. Now you might ask, Dan, why are we doing that here? It's because we're not going to have any recursive calls, just to be very clear. So we need to make sure we put into the queue at least one element. In this case, at least one vertex. Because we're going to have it just simply checking while the queue is not empty. So while there's still a vertex in the queue, as in it's not empty, we're going to do the following. So we're going to dequeue it. So we're going to dequeue from the queue, and we're going to call that V. And then we're going to, now here is where you would do your processing, by the way. So if you had any like processing, you would do your processing here. So if you have anything you need to do to the vertex at that time, this is where you would do it. And then you go through all your incident edges. So we're going to go through all the incident edges again. And then you just simply check. If VW is not labeled, then we check. Is W marked or not? Remember, W is the opposing endpoint in this case. So if it is, then you have a cross edge. If it is not, then you know that you have more to add to your queue, right? So if W is marked, then label VW as cross edge. Otherwise, we do three things. First, you label it. You label VW as discovery edge. And then what you do is you're going to enqueue it, and then you're going to mark it. You're going to enqueue W. You're going to mark W. And that concludes the else block. So that's three things here. Just keep in mind the semicolon here. That closes that. Then we would close the for loop here. Then we close the while loop. I'm sort of abusing my space here. But that's BFS. So notice that it's iterative here. I just presented it that way to you. That way you can get a flavor for how you can imagine, say, DFS. Like, if you, keep in mind it's not literally the same, but most certainly it's very similar conceptually. So now, let's analyze this algorithm. Okay, let's do this. Let's figure out the time complexity here. So for simplicity, I'm going to presume, as I do here, that the graph is connected. Now, as we had with depth first search, do you remember how I told you that whenever I marked a vertex, I never NQ in a vertex that is already marked, right? So you know that every vertex is never coming back into that queue, right? It only goes into the queue exactly once. So observe that the algorithm never NQs a vertex twice. So you're going to see that I'm going to do things a little differently this time. So what I want to do is I want to collect up all of the queue-based operations, and then I'm going to try collecting up all the other work and try to relate it to this while loop here. So I'm going to collect it up into a couple different bins, and we're going to count them separately. So if I were to count up all of the work that happens involving the queues, so like the NQ operations and the DQ operations, and down here we also have the NQs, notice that whenever I give you a vertex, it goes in, it comes out. It never goes back in, right? So all NQ and DQ operations take big O of n time, which naturally, when I say big O, I mean big theta n. Because a queue, you can do these operations in constant time. Now you might ask about how BFS does this stuff now. Now this is where we have to be a bit more careful. Because remember, it isn't a recursive algorithm anymore. So far I've accounted for all the stuff that happens with the queues, right? We know the marking here, all these marking operations, they all take constant time. But what about the incident edges? That seems to be a rather interesting part of this that I have not really addressed, right? So for each one of the vertices, notice that for each vertex, I only at once consider all of its incident edges. And each one, I may label edges and mark vertices, right? But I only do it for the incident edges. So really all I have is two pieces to the analysis here. This part and the other part. So the other part is the steps taken. The steps taken compute the incident edges per vertex across all vertices. So the first part is observing that no vertex is NQ'd twice. So you have just the NQing, DQing taking linear time. Then you have the computation that we see inside of this loop here. So this initialization takes it could take at most linear time, right? To do this, depending on which representation you're using. However, we have the question of what happens with this. So we don't have to worry about this. We don't have to worry about that. So everything else here, notice that it's the incident edges, but all of this can be done in constant time, right? So really, we're at the mercy of this. But we have to do it over all the vertices, right? That's the second part here. But here's the beautiful part. We actually already talked about this when we analyzed depth first search, right? So if we consider when the graph is an adjacency matrix, we consider to compute the incident edges takes linear time, right? We do this for each vertex. So that takes quadratic time. So it takes big O of n squared, or big theta of n squared. And of course, when we consider an adjacency list, actually let me note that right here. So an adjacency matrix it's big theta n squared time, where n is the number of vertices. It's just by the very same reasoning we talked about when we talked about depth first search, just the structure is a little different. It's just this combined with that. So in an adjacency matrix, we have to be rather pessimistic because we have to go through the whole row of a row of the matrix. Sorry, I'm getting very excited. However, in the adjacency list, we have the same predicament with the handshaking lemma, right? To compute the incident edges takes big O of the degree of that vertex. In combination with this, where we consider it over all vertices, that's the sum of the degrees, which is still, that's big theta m. So we combine this with linear time plus big theta m. Well, that's just simply big O of n plus m, or big theta m plus m. So this is no different than the results that we obtained with depth first search. Is that neat? So that's the analysis for, this is my high level analysis here for you. I have more details in the notes, but I'm going to show you just one other detail because I already talked about shortest paths with you. I thought it would be a good idea I talk a little bit about what the purpose of these cross edges versus the forward discovery edges and how that interrelates between the two different types of traversals. Because I think it's helpful for you to see this. So it's just a small little detail I would like to go into. So you know, we talked about there's different kinds of edges. We have the forward or discovery edges. These always form trees in their traversals. So in depth first search, it creates a depth first search tree. In breadth first search, it creates a breadth first search tree. The breadth first search tree, the latter of the two, has a very nice property, for example, that it produces a tree that we talked about that produces shortest ST paths from some source to any other vertex in that tree. So it minimizes the number of edges used for that given path. However, what about the back edges and the cross edges? So let's talk a little bit about this. So in DFS, if I give you a back edge, as I alluded to in one of our applications, if I give you a back edge VW, what it means is that W is an ancestor of V. In the DFS tree. So that's what the back edge actually does. It's actually an ancestor. So like one of the endpoints will be the ancestor of the other one. So that's one thing to point out. So when I'm talking about that, it's an ancestor in the sense of a tree, which means that it may be your parent, it may be a grandparent, it may be a great-grandparent. The point is it's some ancestor. And that's suggested quite nicely when we talked about cycle detection before with depth first search. When we have a cycle, it's because when we detect the back edge, that means we run into an ancestor because it was already marked, right? Okay, in BFS, however, we have it where a cross edge has the following property. So a cross edge cross edge VW, you saw the same syntax, is either on the same level or layer or the next level. This is why we call them cross edges. So let me use this picture. This is why I wanted to make sure I showed you this. Okay, so notice I have my levels. I've sort of circled them here. So I have L0, L1, L2, and L3. If you look at the cross edges, notice that these are either on the same level, so they're among the same bubble, or they cross over into the next one. They never go back, nor do they jump multiple levels. It's always the same level or the next one. Like this, for example, this is going between the two levels. And this is something you would expect, right? Because whenever we take one step, like if hypothetically speaking, if I could get to this one within less steps, I would have taken it in my breadth first search. I'm just saying. If it was multiple hops, it would have been closer, akin to what I do here. But the reason why it's in the next level is because I already had another edge here. Okay? So that's your explanation for a back edge versus a cross edge, and their purpose is between the two different types of traversals. Is that neat? Yeah, so I told you about shortest paths. I didn't prove it for you, but if you look at the vertices at any one level, you can count up the number of edges that go from one level to another based on the level number. So that's something you can actually prove using mathematical induction. And it's actually that's part of at least one way of proving the claim that this actually produces a shortest path tree. So just as a fun little remark, just because I feel like mentioning it for you, I'm just going to get the chat open. One fun little remark I'll mention to you is, if you ever heard of Dijkstra's algorithm, which is an algorithm I do plan to cover properly at one point. I have previously in this channel. If you go to Dijkstra's algorithm, you might ask, Dan, how exactly does Dijkstra work in relation to these graph traversal algorithms? Well, you actually think about it, it's actually an adaptation of breadth first search, because it uses the same property of computing a tree, but also it uses this fact that you can take steps through the graph like this level by level. But the thing is, it uses distance labels that use in combination something called an edge relaxation. And the edge relaxation is what guarantees that the shortest paths are guaranteed in that version of the problem where you actually have distances that are numbers, not just unit lengths. But yeah, that's just a whole other remark altogether. Are there any questions or anything like that? I'm really happy to answer any questions. But that's everything I have to say about graph traversals, at least for today. I plan to talk more about this topic in the future. If, say, for example, there's any claims I made here that you're curious about, I'm most certainly planning to go into more detail if, say, there's certain things that interest you. If you're watching this in the future, for example, just put in the comments, let me know. Or just like send me a message or something. Hey, look, Dan, this thing that you told us in the class or lesson, I would love to hear more about it. Like, can you tell me more? Like, how do you know that that's true? I'm happy to do that. I'm happy to go into those nitty gritty details. That's one thing I really like doing. But yeah, no. If there's any specific questions, I'm happy to answer them. Of course, if there aren't, I can stick around for another minute, but most certainly it was a pleasure hanging on out with everybody. So if you got to go off and go do something, I plan to not cover any more other things unless there's any questions, at least for today. But yeah, no, I'm planning to cover more graph algorithms, more of these topics, and most certainly one thing I'm planning to do, especially towards the end of the month, is I'm planning to talk more about reductions. So I plan to try to build more of a catalog of your basic stuff and your more advanced stuff. I know that I've heard from some people that aren't necessarily subscribers, but most certainly have interest in being a part of everything, that they'd be interested in seeing a proper series on advanced algorithms. So I'm talking about like flow networks, approximation algorithms, randomized algorithms. I'm planning to cover something akin to this in the near future, which I'm really excited about, by the way. I was developing a curriculum quite similar to this before. So I'm actually quite happy to explore this option. If, say, that sounds interesting to you, let me know. I'm planning to go through a proper, like, full-blown walkthrough of a lot of very important, what I would consider modern theoretical computer science issues. So things ranging from, like, sure, when I say modern, I mean, like, last 20 to 30 years. So you have to learn the fundamentals to understand a lot of that kind of stuff. So I plan to cover a lot of the kind of like, oh, you want to learn what an approximation algorithm is versus a randomized algorithm, like what is an online algorithm. I'll be planning to talk about all of these things eventually. Just let me know if that interests you. That is something I'm really excited about. But yeah, no, it doesn't seem like we have any questions. I was just looking at the chat. But yeah, no, it was a pleasure to have everybody come on down. So again, as per usual, tell your friends to come on out. It was nice seeing some more faces around. I appreciate it. I love the lovely questions, especially the interactions. This is really helpful for the discussion. It always makes every discussion a little bit more fun, and I like to have lots of fun here with everybody. So if you like this, make sure you subscribe and follow. Tell your friends to come on out. More people here, the more fun we can have. And of course, if you like things beyond that, or you want access to the notes that I've talked to you about here today, you can access those on Patreon through patreon.com/pagewizard. Specifically, the things I covered here today, you can find them in my book, Advanced Data Structures, An Introduction to Data Structures and Algorithms. I'll grab the book one more time. You can find it on Amazon, Google Play. You can also buy this physical version. I am actually currently working, at least I'm planning to work properly on the second edition, which will be a hardcover. And it'll also be filled in. Right now, the first edition is a collection of notes. The second edition may actually be more textbook-like. But to keep in mind, if you're looking for something to accompany some of the video series that are on the channel and some of the stuff I do cover, this is a helpful resource for some of the examples I do here. But most certainly, that's something out there in the wild. I like to make my content very affordable for people. That's one big thing for me. So you aren't paying lots and lots of money for the things I do. It's very much like, because I always look at it the way I did, because I'm a first generation academic. I was very first in my family to do a lot of the things I do. So for me, it's very much, I see it as paying it forward, you know? And at the same time, it's also that I want to get people excited about theoretical computer science, because a lot of this stuff serves as a beautiful backbone for much of what's out there in the wild. And knowing a lot of this stuff can help give you more insights into, if you decide to go into some more advanced study of computer science, how exactly, like what are the underlying phenomena that you encounter in a lot of these areas. And learning about a lot of this stuff could be very helpful for that. But right now we're kind of doing the fundamentals, which I'm really excited about too. Believe me, I'm obsessed with graphs. So anyways, with that being said, I want to say thank you so much for coming on out, and have yourself a beautiful day. I'll see you later. Have yourself a beautiful day. Sorry, I had to say it again. I'll see you later.